piecewise defined functions like this one, we're going to be concerned about limits and continuity in a few minutes at places where there are holes or jumps in the graph. Basically, if there is no hole or jump in the graph, you can find the limit by simply plugging into the equation of the function if we have it, or just by looking at the value of the function on the graph. But when we have holes in our graph, then things change a little bit. So let's take a look at the first question. So we have on the right here, true or false, the limit as x approaches -3 from the right, the little plus sign that's in the position of a superscript there. Maybe I should zoom in on that. That little plus sign there, that indicates from the right. So the limit as x approaches -3 from the right of f of x is equal to 9. Okay, so let's go back to our graph. We're looking at the limit as x approaches -3 from the right. Okay, so first thing you need to do is to find the x value -3, which is here, and then just kind of look up or down to the graph to see where it comes in contact with that value. Okay, so it looks like to me hold on, I'm just checking my chat here. Okay, no questions so far. All right, so it looks like to me that this dot is exactly lined up with the x value -3. But limits are not about what happens at that point, but what happens near it. And more specifically, since it's a limit from the right, then we're going to stay in a neighborhood of that point nearby, but we're going to follow along the graph on the right side, going towards the x value -3. So we're headed towards this point, but we're following our finger along the graph here, right? So if I follow along the graph, I see that I'm headed towards the y value 9. Okay, so that's all it is. That's all they're asking us to look at, is what point is it headed towards. So it was headed towards the x value 9, so it looks like that would be a true statement. All right, now let's look at the next one. How about the limit as x approaches 0 from the left? Again, this superscript here, it's in the position of an exponent. That means a negative indicates from the left and a positive indicates from the right. So we're talking about from the left side of that point. Can't really read that. Let's see. So this is a left-hand limit. Okay, so we're going close to the x value 0 coming in from the left. Let's look at our graph. All right, so we find the x value 0. Okay, and at the x value 0, where we see this open dot here, and then a closed dot up above it 4. But remember, a limit is not about what happens at the value, but what happens near it. And we were asked to come in from the left. So you get close to the x value 0. We say we're in a neighborhood of the x value 0. Somewhere nearby, following along the graph coming in from the left side. So if you can picture your finger following along this graph, what we're interested in is which y value it's headed towards. Now this is the point 0, 0, so the y value and the x value are both 0, but we're just interested in the y value. We already know the x value is 0, that's the reason why we're looking here. But the y value that we were headed towards was 0. Now the graph doesn't actually end up at 0, it ends up at 4, but again, a limit is about what was happening near it. In other words, if we made a table of values, we would see that the y values are getting very, very close to 0, although they never actually reach 0. But it would reach a number like 0.01 or 0.001, for example. All right, so this left-hand limit is 0, which they said the left-hand limit was 4. Remember, that was the function value, not the limit. So let's see if false is correct. Yep, false. Okay, let's go ahead and look at the next one. Remember that you can type in a question at any time, or if you have my Skype, you can text it to me that way as well. All right, so the limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right. Is that true or false? Well, we already figured out that the limit as x approaches 0 from the left turned out to be 0. Let's go back to the graph and see what the limit as x approaches 0 from the right would be. So on the right-hand side, I'm going to highlight it in green instead of yellow. We're talking about this side of the graph. And if you imagine following along with your finger along the graph in this little green area going towards the x value 0, then we're going to end up at that open dot again, right? Which has a y value of 0. So that means that the limit from the right is also 0. So 0 does equal 0, so that's true. Okay, so that's let's look at a couple of other examples. Same item on my math lab, but there are a few more parts. So I just copied the graph down again. So let's scroll down. Okay, so same function. This time, let's see what they ask. The first question is, true or false, the limit as x approaches 0 exists. For that one, I don't need to look at the graph. I know that the limit does exist because we just found that the limit from the left equals the limit from the right. That's what we saw up here. Up here. The limit from the left as x goes to 0 equals the limit from the right. And so if that's true, then we know that the limit exists. And we found that they were both equal to 0, which means that's what the overall limit is equal to as well. So there goes those two items. Thank you for posting, Lisa. Okay, so next we're going to look at true or false, the limit as x approaches 3 of f of x equals 9. Okay, so in order to find the limit as x approaches 3, we're going to look at the graph here and see if anything odd is happening at the x value 3. And we see there is, in fact, a break in the graph at the x value 3. So when that happens, you look and you see, does the limit from the left equal the limit from the right? So coming in from the left towards the x value 3, we're going to hit the y value 9. Well, actually, we don't ever actually hit it, but we're headed in that direction. And then, of course, there's a break in the graph. But again, and I can't say this enough, the limit is about what's happening near the x value, not what's happening at the x value. So coming in from the left, we're headed toward 9. Coming in from the right, however, we're looking at this horizontal line segment down on the x-axis. And as we come in from the right, we're headed toward this closed dot, which has a y value, remember y value, not x value, a y value of 0. So, is it true that the limit as x approaches 3 of f of x is 9? Well, it's true that the limit as x approaches 3 from the left of f of x is equal to 9. But the limit as x approached 3 from the right of f of x was actually equal to 0. And if the limit from the left doesn't equal the limit from the right, then that means that the limit overall does not exist. So this should have been does not exist. So the answer here is false. Okay. And then there's one more. We have the limit as x approaches 6 from the left. The limit as x approaches 6 from the left. So we find the x value 6 on our graph. Okay, we're talking about coming in towards that value from nearby along the graph. So we're not going to jump over to that parabola shaped part of the graph, for example. And then coming in from the left, we're headed toward the y value 0. So the limit as x approaches 6 from the left is not 6, that's false. Okay, all right, so that was the first question in 2.4. 2.4.1 is the question ID. And by the way, I'm writing this solution in our OneNote. So if you want to go back and look at it, not only will it be recorded and I'll post the link to the live chat, but also you can just look through it right here. Okay, I have a question from Lisa, and she asks if I can work some problems from 2.1, specifically items 5 through 8 she's interested in. Let me see if I have 2.1 in here. Let's see. Okay, I do have the solution to number 8 posted in the OneNotes. That code for that one is 2.1.15. I go by this 3-digit number, not 3-digit, but this 3-part number here on the left, because that tells you the chapter section and what would have been the item number in the ebook. But let me do a different one. Let's see. All right, let's just start with item number 5, which is 2.1.8. Okay, so here we're going to find the slope of a curve at the given point P. And by the way, the slope of a curve is like what calculus is about, especially calculus 1. So this isn't going away. We will learn some shortcuts for finding the slope of the curve at a point, but this covers the basics. And in this section, you're actually using, to find the slope of the curve, you're using a specific formula called the limit of the difference quotient. So let me go ahead and write that down. So in this problem, you're going to need to know that the slope of a curve which, by the way, when you say slope of a curve, it's equivalent to saying the slope of a tangent line to a curve. Those mean the same thing. the slope of a curve at a point x equals, well, let's just say at a point x for now. At a value x is given by the limit of the difference quotient and what I mean by that is the limit as h approaches 0 of the quantity f of x plus h minus f of x all over h. This also happens to be called the derivative, and the notation we use for the derivative is read f prime of x, or it's called the derivative of f. Okay. So anyway, we need to be able to find the difference quotient, which is going to give us the slope of the tangent line for any x value we plug in. And we're in part B, we're going to have to find the equation of that tangent line as well. So part A is going to help us with part B because we're going to get the slope. So let's go back up here. What are we trying to do here? We're trying to find the slope of the curve y equals -1 minus 9x squared at the point where x is 5 and y is -226. Okay, so what we're going to need from this part is just that x is 5. What we're going to need from this part is to take the limit of the difference quotient for that function. Now I use function notation for my formula for the limit of the difference quotient. So what you might want to do is to think of this in terms of function notation. Instead of y, think of it as f of x equals -1 minus 9x squared. And then the formula makes a little bit more sense. Okay? I don't see any more questions so far, but remember, you can't, if I say something that you're not sure about, you can always ask. Okay, so I'm going to now plug in and find the limit of the difference quotient. Remember, when you do this, you're going to have to plug x plus h into the function f. All right, so let's work that out. I'm going to rewrite my function f down here. Yeah, okay. And now I have f of x, and now I want to find f of x plus h because I'm going to need it for the limit of my difference quotient. Now what I usually say is, because sometimes it confuses people to plug x plus h in for x, because there's x's in both expressions, people get them confused. Just think of this x in the original function as a little box, and you're just plugging into that box. So we're going to have -1 minus 9 times, instead of the box, x plus h squared. All right, another area where people have trouble is simplifying this. So before we actually plug it into that big formula with the limit, let's just work with this. So first of all, when you square a binomial, you have to FOIL it out, or you have to be familiar with the pattern of a binomial squared. To get a binomial squared, you're using the pattern a plus b squared equals a squared plus 2ab plus b squared. So you always get the first term squared, the last term squared, and twice the product in the middle. So one little rhyme you can remember to speed this up rather than foiling it all out is square the first, square the last, multiply together, and double up fast. So I'm going to square the first term, gives me x squared, plus I'm going to square the last term, which gives me h squared. And then I'm going to multiply these together, which gives me xh, and double it, so 2xh. So that's a nice little rhyme one of my students taught me. Let's go ahead now and distribute that 9, -9 actually, through the parentheses, and we have -1 minus 9x squared minus 18xh minus 9h squared. So that's what f of x plus h is actually equal to. That's just part of the limit of our difference quotient. All right, the next thing we're going to need is to subtract f of x from that. So before I go and put it all into that big fraction, let's just figure out what would f of x plus h minus f of x be equal to. So I'm going to take the f of x plus h that I just found and copy it down, and I'm going to subtract from that in parentheses the original function f of x, -1 minus 9x squared. So distributing the negative through, and we're going to be able to combine some like terms here. And what you should see is that anything that doesn't have an h in it usually cancels out. So let's see, we have -1 minus 9x squared minus 18xh minus 9h squared plus 1 plus 9x squared. So the -1 and the +1 cancel out. They add to 0. -9x squared plus 9x squared, that adds up to 0. So all we're left with is -18xh minus 9h squared. That's going to be in the numerator of the limit of our difference quotient. So I'm going to rewrite, since it's not on the screen anymore, I'm going to rewrite the limit as h goes to 0, f of x plus h minus f of x over h. Remember, this is called f prime. That's our derivative. And this is going to be equal to the limit as h goes to 0 of, and now I'm just going to take this guy here and put him in the numerator, because we already figured out all the simplification of the numerator that we need. It's still over h though. Now, to find a limit as h approaches a number, you would want to see if you can plug in that number, but in this case it's not going to work, because we would get 0 minus 0 over 0, and 0 divided by 0 is an indeterminate form. So in other words, we don't know from that whether the limit exists or not. So what we would like to do is a little algebra to, if we can, cancel that h from the denominator so we no longer have division by 0. So factor out from the numerator, factor out an h. You can factor more out if you want to. We certainly have more in common there. But all I really need is to factor out that h in order to be able to cancel it with a factor of h in the denominator. So h divided by h is 1. 1 times -18x minus 9h is just itself. So we have the limit as h goes to 0 of -18x minus 9h. And now we check again. Can I plug 0 in for h? Yes, I can. That would give me -18x minus 9 times 0, which is -18x. That's not an indeterminate form anymore, right? So we have found our formula for slope. The slope of that particular function at any particular x value. So if we want to know the slope of the tangent line to f of x equals -1 minus 9x squared at, I believe it was the x value 5, wasn't it? Yep, they were asking us about the x value 5. We want to know the slope of the tangent line to that curve at x equals 5. The shorthand notation for that is just f prime of 5. This formula, remember, was f prime of x. So we found that f prime of x is just -18x. That's the formula for the slope. So if I plug in 5, I get the slope at 5. So that's going to be -18 times 5, which is going to be what, -90? All right, so I'm going to go back to my exercise here since I have it open. Let's see if I got it right. 90. Oops, I put 90 instead of negative. -90. Okay. All right, so then the next part is the equation for the tangent line at the point P, where the point P, remember, was 5, negative 226. So part B, that's the answer to part A. Okay, now part B, we want to find the equation of the tangent line. And that is at 5, negative 226 through 5, negative 226. All right, so when you're finding the equation of a tangent line, well, when you're finding the equation of any line, you need the slope and you need a point on the graph. Some way, shape, or form, the information you have must be able to be whittled down to a slope and a point. So in this case, we have our point, right? And we just found our slope. Our slope is negative 90. So I know in my math lab, it shows you this method where you plug into the point slope form of a line, y minus y1 equals m times x minus x1, which is a great method, and if you want to use it, that's fine. You just have to make sure you've memorized that formula. But I prefer to use y equals mx plus b because students usually remember that one. And all you need here, you have an x value, you have a y value, that pair must satisfy this equation. We have m, and we can just find b. So I'm going to plug in negative 226 for y, and I'm going to plug in negative 90 for m, and I'm going to plug in 5 for x, and I'm going to solve for b. So that gives us that negative 226 is negative 450 plus b. Adding 450 to both sides, this is going to give us, 224 for b. So that means that our equation is y equals negative 90x plus 224. And again, since I happen to have that exercise open, let's go ahead and type it in. So y equals negative 90x plus 224. Okay, so yeah, so we got that one right too. Oop. Okay. Let me ask Lisa, do you have a particular problem besides number 5 that you wanted to work? Number 6 is this one where the curve, the steps are the same. The curve is y equals x squared minus 3x minus 2 or something similar to that. And number 7, the curve is y equals x cubed plus 3. And then number 8 is the one that I have already posted a video and the worked out problem. So were there any of those other two? Were there either of those others that you wanted to look at? Or are you okay now? Eleven. Okay, is this the item 11 that you're referring to? Oh, my mistake. You're right. That's number 10. Let me go to one more. Okay, here we go. Number 11. All right, so it says the accompanying graph shows the total amount of gasoline in the gas tank of an automobile after being driven for T days. And the first part of it is estimate the average gasoline consumption over the time interval from 0 to 3. Okay. So well, first let me take a picture of this. Okay, and now I'm going to just make it a little bit bigger. Let's see here. Do I want to do it through here, maybe? I don't think that's that much bigger. Maybe a little bit. Okay, so first of all, what does average gasoline consumption mean? So we have a chart here that tells the remaining amount in gallons. And the rate of time elapsed in days. Oops. Okay, and so whenever you see average consumption or average rate of any kind, we're just talking about a slope between 2 points. So average rates, an average rate equals a slope between 2 points. Okay, average rate of change, I should say. Average rate of change. Okay, so going to the interval 0, 3, what's that referring to? So we're looking at the x value 0 here, and then the corresponding y value is 18. So on our graph, we go through 0, 18. And then at 3, if I follow that on up there, that appears to be 3, 15. Okay. So average rate of change between these two, if you want to think of it that way, is the slope of the secant line that would run between those two. But we just want to think slope is y2 minus y1 over x2 minus x1. That would give us our value. So 15 minus 18 over 3 minus 0. It's going to give you negative 3 over 3, which is negative 1. All right, so the numerator of this fraction, since we were subtracting y values, is units of gallons. And here we were subtracting x values, which was elapsed time in days. And so we have negative 1 gallons per day. We've gone down, our remaining amount is going down by 1 gallon a day. So in the question, the average consumption is how many gallons a day? Well, if the amount that we have left is going down by 1 gallon a day, that means our consumption is 1 gallon a day. So since we have this open, let's go back here and put in a 1. Okay, so 1 gallon per day. Now it says estimate the average gasoline consumption over the time interval 0 to 5. So let's go back to our graph here. Let me put a 1 in here. Okay. Now from 0 to 5, we're talking about the point 018 again, but let's maybe do blue ink, or actually let's do green. All right, so we're going to do that point again, 018, but then we're doing 5 and whatever line this is. That appears to be 11 there. Okay, so again, average rate of change is the slope. So this one was, well, slope 1. Let's do slope 2 here. And this is going to be 11 minus 18 over 5 minus 0, which is going to be negative 7 over 5, which is going to be, let's see, negative 1.4 if you do it as a decimal. Let's see how we want our answer entered into my math lab. Type an integer or decimal. Okay, so it's going down by 1.4 gallons per day at this point. Okay. Estimate the average gallon consumption over the time interval 7 to 10. So from 7 to 10, let's go with red ink here. 7 looks like is at 9. The y value is 9. 10, it looks like 6. So 10, 6. So the third part is going to be 6. The y2 minus y1, right? So 6 minus 9 over 10 minus 7. So that's going to be negative 3 over 3, which is negative 1 again. So from day 7 to 10, the average is, or I should say from 7 to 10, the remaining amount is going down by a gallon a day. So that means that we're using a gallon a day. Okay, now they want us to estimate the instantaneous rate of gasoline consumption at the time t equals 1 in gallons per day. Okay, so to estimate the instantaneous rate of change means estimating the slope of the tangent line. I'm going to just get a new graph here. Copy this over. Oops. Okay. So at t equals 1, we're going to imagine drawing a tangent line to the curve. So down here is t equals 1. We got to follow it up to, it looks like about this here. All right, so we're going to draw in as straight of a line as we can that only touches the curve at one point. So for example, this wouldn't work because it's going right through the graph. Let me see if I can flatten it out here. And on your paper, of course, you can use like a ruler. You can probably do better than me, but I guess you would have to maybe print it out, would probably be the best suggestion I could make. Okay, so this looks like, and again, this is an estimate. Oops, here we go. Okay, so this line that I just drew in red appears to only touch the graph at that single point. So this is a tangent line. Okay, so let's see what it looks like the slope of this tangent line is by using rise over run. Let's see, maybe extend it a little bit. Let's see if we hit anything. Oh. If I can extend it without messing it up. I don't know. I don't see where it's hitting any nice even values. So let's just guesstimate here. So here 17, this is 18. So it looks like the y value of this first point, which remember t is 1, the y value appears to be about 17 3/4, 17.75. Okay, and then we'll find another point somewhere along here, maybe here. So this one looks to me like, first of all, the t value is 4. And then the y value looks like it's about 15.75. All right, so to find the slope of this tangent line, estimate the slope of the tangent line. Okay, the fourth slope we have found, 15.75 minus 17.75 divided by 4 minus 1. And let's see, that's going to give us -2 over +3. So -2/3. So about -0.67-ish. Okay, so let's see, what were our options again? Oops. Oh, -0.67. Wow. I would not expect that my calculation would be so accurate. But what I would expect to get is something like, -0.5. Anything that's smaller than 1 and negative, that's kind of how I would break down the slopes here. Is like, if I got a slope that was between 0 and 1, I'd pick this one. If I got a slope bigger than 1, I'd pick this one. If I got a slope bigger than 1 but negative, I'd pick this one. And if I got a slope that was negative but small, something between 0 and 1, I'd pick this one. But ours just turned out really nicely. Okay, so I don't know, do you think that that makes sense now, Lisa? Okay, good. Did you have any other questions? Okay, I'm going to go ahead and look at item number 2.4.3 unless anybody has any other questions. And yes, to answer your question, Lisa, you can watch the recorded version of this video, of this live chat at any time. I will be posting the link to it here in this OneNote. If you come and look at OneNote, which it might look slightly different depending on which version of OneNote you're looking at, but basically you're going to look for a tab for live chat recordings, and then look for live chat week 1, live chat, that should actually say week 3. So look for a live chat week 3, and right here I'm going to have a link to the recording. So I'll post an announcement when that is there. Okay, so I'm going to continue talking about left and right-handed limits for a little bit, and then maybe some continuity as well. So using the following function and its graph, we're going to answer several questions, A through D. So in this first part, we're being asked to find the limit as, and I really don't need that there. We're being asked to find the limit as x approaches 4 from the right, and the limit as x approaches 4 from the left. And so notice that 4, the x value 4, is where something strange occurs on the graph. So that's often one, a situation that you'll see when you're being asked to find a limit from the left and from the right. This is actually a piecewise defined function, and you can see the formula for this piecewise defined function. And you see how whenever we define a piecewise defined function, there's going to be boundary values where the equation changes. So this boundary value is always going to be important, and it's a potential discontinuity. As you can see here, there is a discontinuity there. So we'll be talking about continuity in the next section, next few problems actually in this section. And so what can happen there is the behavior of the function on the right side of 4 and the behavior of the function on the left side of 4 can be different. And that's why we're concerned about what's happening at 4, or near 4, I should say. Okay, so what's the limit as x approaches 4 from the right? Remember, we're just going to be very near to 4, but coming in from the right, we're headed towards the y value 5. This would have been the point 4, 5, but we have an open dot there. So that's why they say the limit as x approaches 4 from the right is 5. On the other hand, coming in from the left side towards 4, you're going towards that lower dot, which has a y value of 4. So that's why they say the limit as x approaches 4 from the left is 4. Okay, so based on that information, let's answer this question. Does the limit as x approaches 4 of f of x exist? And the answer to that would be no, because the limit from the left does not equal the limit from the right. We found different, the graph was headed towards different y values, giving you this jump discontinuity, as we'll call it, in the graph. So the graph is not nice and smooth, there's a jump in it. Okay, same graph, same function. What about the limit of f of x as x approaches 6 from the right? The limit of f of x as x approaches 6, and the limit of f of x as x approaches 6 from the left. 6 from the right and 6 from the left. All right, notice 6 is not a boundary value. So when you have a piecewise defined function, and especially when your functions are all polynomials or other nice smooth curves, if it's not a boundary value, there's really not any question. You're going to just plug in and find the limit as x approaches 6. In this case, we could look on the graph, so let's do that first, but then we'll see that it's going to be the same thing if we just plug in. So the limit as x approaches 6 from the left appears to be 6, and the limit as x approaches 6 from the right appears to also be headed toward the y value 6. And so we would say that the overall limit as x approaches 6 of f of x is 6, right? The limit from the left equals the limit from the right. And they both turn out to be 6. That means the overall limit is 6. Now, we could have, since this was 6 was not a boundary value, what would we have gotten if we evaluated f of 6? Well, 6 is greater than 4, so we would have gotten 6 over 2 plus 3, which is 3 plus 3, which is 6. And since these are two polynomial functions, those never have any, like they're not like rational functions where the denominator can be undefined. They're never going to have any problems like that. So since 6 is not a boundary value, you could just literally plug into the function and find that result as well as looking at the graph. And next we're going to look at 2.4.4, similar problem. It says use the following function and its graph to answer parts A through D below. Part A asks what's the limit as x approaches 3 from the right. Let me zoom in a little bit, make sure you can read that. It looks kind of small. So this is the limit as x approaches 3 from the right that we're being asked about. So again, on our graph, the limit as x approaches 3 from the right is saying find the x value 3, and what y value are we headed towards if we follow along the graph coming in towards 3? We're headed towards that open dot. And that open dot appears to have a y value of 1. In fact, we are looking at x values greater than 3, which means that this rule would apply here. Notice that if we plugged in a 3, which our function, when you have a function x value of 3, you have to plug into the rule that says y is 2. But let's pretend for a moment that that weren't the case. If we did use this rule to find the y value when x is 3, we'd have 3 over 3, which is 1. That's not a coincidence. That's how we get that open dot right there. We would have had a point there equal to 1, but our function is piecewise defined and tells us that that moment that we get to 3, y is equal to 2. Okay. So anyway, coming in from the right, we're headed towards 1, no matter how you look at it. So the limit as x approaches 3 from the right is 1. All right, part B asks, or the next part asks, find the limit as x approaches 3 from the left. All right, so the limit as x approaches 3 from the left means follow along the graph coming in from the left. That's one way to think about it. Notice we're still headed toward that open dot that has a y value of 1. So that would be enough to conclude the limit from the left is 1. But also I just want to point out that x is less than 3 here for these values that we're considering. And if you have values less than 3, we're working with this rule on the top here. Now again, at 3, we jump to the middle rule where telling us the y value must be 2. But let's suppose for a moment we had been able to plug 3 into this rule. What would we have gotten? A 1 again. So you can actually find the limit from the left by plugging into the rule from the left. It doesn't actually reach that value, but it would have if we had kept going. So anyway, back to this question, finding the limit from the left turned out to be 1 again. So the next part of the question says, find f of 3. All right, well, f of 3 is referring to the y value at 3. So you can see on the graph that the y value at 3 is going to be 2. But you could also see that by plugging in to the function. The equation for the function is this big complicated thing here, and it says when x is 3, the y value is 2. So 3, 2, when x is 3, f of x, or the y value, is 2. So coming back to this part down here, we want to know what is f of 3. It's equal to 2. This is what's called, by the way, as we work our way up to it, a removable discontinuity. We have a hole in the graph, but if we could have just redefined that one point at that one x value 3, if we let that be a y value of 1 instead of 2 over here in the way we defined our function, we would have had a function that we could draw without lifting our pencil off the paper, and that would have been a continuous function. We'll see. We'll be working with here shortly. Okay, next question, same item, but we're looking at a different part of the problem now. It asks us to determine if the limit as x approaches 3 exists. So remember, in order for us to have a limit exist, the limit from the left has to equal the limit from the right. But we just found that in both cases, in both sides, we are headed toward a y value of 1. So the answer to that is yes, and it's equal to 1. So in order for a limit to exist, it must be that it exists on the left and the right, and it's equal to the same number in both places. Okay, so let's go to part C, same function. Find the limit as x approaches 2 from the right. All right, so the limit as x approaches 2 from the right. Notice that on this piecewise defined function, 2 is an interior point of one of the nice smooth parts of the graph. In other words, it's not a boundary value. But so nothing weird should happen. So that should mean that the limit from the left, the limit from the right are the same, and that they're both equal to the function value at that point. So if you plug in 2 to the function f, you should see that you get a 2 for y. Let's see. To plug in 2, we're using the rule where x is less than 3, which would give us 4 minus 2, which is 2. Yeah. So no matter how you look at it, the limit from the left equals the limit from the right equals the limit, which is the function value, which is 2. So if you're asked about any of those facts, you're going to get a 2. Okay, so limit from the right is 2, limit from the left is 2, and then I believe in the next part they ask us for the overall limit. Yes, the limit exists and equals 2 because the limit from the left equaled the limit from the right. Okay. All right, so anybody who's still watching, if you have any other questions, you can ask me at any time. All right, here's one where they didn't give us the graph, and I wanted to look at one of these where the graph was not given, because it's, you know, harder maybe to visualize. So here we're told to graph 1 minus x squared where x is not equal to 1, and 4 when x is equal to 1. Find the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. Does the limit exist? Okay, so when you're asked to graph a piecewise defined function, what I like to do is to make different f of x charts for each piece, especially until you get used to making these graphs. And this one is going to be true for any x values that are not equal to 1. So what I'm going to do is, since this is a boundary value, I'm going to put the 1 on my list of x values, and I'm going to circle it to remind myself that there's going to be an open dot there. And then I'm going to pick other values nearby, like 0 and 2. Okay, and plot those points. I know this should be a parabola that opens downward. And you should be familiar enough with this to know where the vertex is going to be in the x-intercepts and everything. The vertex, this parabola maybe is more understandable as far as transformations go if you think of it as negative x squared plus 1. Coefficient of x squared is negative. We have a upward shift of 1. So we would expect it to be right in the center of our xy coordinate system. But anyway, let's go ahead and plug in 0, and we get f of 0 is going to be 1. Plugging in 1, we get f of 1 is equal to 0. Again, this point is not actually necessarily on the graph because we're not supposed to use this rule when x is 1, but we use it nearby, so I'm going to go ahead and include it. And then f of 2 is going to be 1 minus 4 is going to be negative 3. Okay, so I'm going to start by plotting those points. Oh, you know what I forgot? We have a nice little XY chart here. Okay. All right, so we're going to go through 0, 1, which would be here. We're going to go through 1, 0, but that's going to be an open dot. And we're going to go through 2, negative 3. 2, negative 3. All right, so if we just went based on this, a lot of students would plot a line. So we don't want that. But remember, we did know that it was going to be a parabola shifted up, shifted up 1 unit. So the vertex is going to be up at 0, 1. So this is only half of the shape that we're looking for, right? It's going to also have a mirror image on the other side. Okay. And then we're going to plot the rule for x, f of x equals 4. Now, normally we have something more complicated than just a constant, but we know that this rule only works when x is equal to 1, so all this is representing is the point that 1, 4 is on the graph. So 1, 2, 3, 4, so here's 1, 4. Okay, so here's our graph of our piecewise defined function, and we were asked to find the limit as x approaches 1 from the left. So coming in from the left towards the x value 1 means following along the graph this way. We're headed toward the y value 0. So the limit as x approaches 1 from the left is 0. Coming in from the right, we're also headed toward that open dot that has a y value of 0. So this is going to be 0 as well. So when they ask you, does the limit as x approaches 1 of f of x exist? You can say yes, because the limit from the left equals the limit from the right. And they're both equal to each other. I guess that's what I just said. Okay. All right. Okay, this one I just wanted to mention that this is only going to have discontinuities when you have negative numbers. or when you have x equaling -3, and that gives you 0 in the denominator. So this point where x is -0.25, we should be okay because we don't get negative values, and we don't have a -3 giving us an undefined in the denominator. So you don't really need to graph this guy in order to find this limit. To say that in a much more formal way, this thing is going to be I'm going to start using the idea of continuity. It's going to be continuous, and when I say that, what I'm basically, since we don't have the formal definition of continuity at this point, what that means is that the function is nice and smooth. It might have some sharp points, but no gaps in it. Okay, so it's continuous as long as x does not equal -3 on its domain. So for any x values that are allowed here, unless there's n points on its domain, and then it's going to that means that the limit will exist everywhere on its domain, except at the endpoints of the intervals of its domain. It might only exist from the left or from the right. So let's go ahead and take a look at what its domain would be. We can only take the square root of numbers that are greater than or equal to 0, because these are all real valued functions. And so you might recall from pre-calculus and college algebra that we can solve an inequality like this by analyzing a sign chart, because this means positive or 0. So what I can do is I can look at any important values where the sign might change, and that can happen when the function is undefined or when it is 0. So it's 0 when x is -14. So I have x values on the bottom, and then the numbers I get from plugging into the expression on the top. So when x is -14, we could get 0. And when x is -3, we get undefined. These are places where the graph potentially changes from positive to negative. And remember, we're interested in that because we only can take the square root of negative values. Anyway, if you plug in a value on each of the intervals, -15, -5, and 0, for example, I'm just making up those values, you're going to see you're going to get negative over negative. Negative divided by negative would be a positive. When you plug in -5, you're going to get a negative divided by a positive, so that's going to give you negative values. And when you plug in 0, you're going to get a positive divided by a positive, so that's going to be positive values. All right, so the domain of this function is going to be -infinity to -14, including -14 because the value 0 is all right, union with -3 to infinity. Or if I were to draw it on a number line, it would be these pieces here, right? Okay, so where is -0.25 on these intervals? It's on the interior of these intervals where we know that the curve is going to be nice and smooth. So you can just plug, it's not, if we were plugging a negative, if we're trying to find a limit as x approach -3 or a limit as x approach -14, this would be more complicated. But it's not a boundary value, so you can just plug in. In other words, the limit from the left, the limit as x approaches -0.25 from the left of this crazy looking function is the same as the limit as x approaches -0.25 overall. Remember, in order for the overall limit to exist, these must be the same, and I know it's going to exist because it's on the interior of the interval. So all you have to do is plug in. So that's going to be the square root of -0.25 plus 14 over -0.25 plus 3. So getting out your calculator. We have 13.75 divided by 2.75 equals 5. So we have the square root of 5. Which is what it's supposed to turn out to be. Okay, so I know that sounds really complicated, but the moral of the story here is that unless you have a boundary value, a value that makes the function undefined, or the end of one of the intervals in the domain, you can just plug that x in and get the limit, because there's no holes or gaps there. Okay, here's another one that I thought you might want to see, and this will be the last thing for today, and then I'm just gonna leave you to it. Okay, so we're trying to find the limit as age approaches 0 from the right. Actually, you know what? I'm sorry, guys. It's 5 o'clock, so I've got to go. But I'll post the solution to this in written form in your OneNotes. So thank you for watching, and if you found it helpful, go ahead and give the video a thumbs up. That helps other students to find the video. Oh, and by the way, just because I'm not on the live chat doesn't mean you can't contact me. You can email me or Skype me.